lecture, we are diving into the world of cold rooms and the role they play in preserving food. We'll also touch on the basics of refrigeration systems design to ensure efficient and effective operations. So what exactly is a cold room? A cold room is essentially a giant fridge used in food industries for the production and storage. It's designed to maintain a specific temperature, typically ranging from plus 15 Celsius degree to minus 40 Celsius degree, depending on the content to be stored and the specific requirements for preserving those items. The rooms are insulated to minimize energy consumption and to prevent temperature fluctuations, guaranteeing the safety and freshness of the stored goods. Several types of cold rooms are available, depending on the specific needs. For instance, there are cold rooms, also known as positive temperature cold rooms, which maintain temperatures between 0 Celsius degree and plus 10 Celsius degree, ideal for storing fresh products and beverages. On the other hand, freezing cold rooms operate at colder temperatures between 0 Celsius degree and minus 28 Celsius degree, designed for preserving frozen foods like meats and seafood. Finally, there are deep freezing cold rooms, which work between minus 30 Celsius degree and minus 40 Celsius degree, and blast freezers that quickly reduce the temperature to minus 40 Celsius degree, minimizing the risk of contamination. A dedicated refrigeration system is essential to keep these cold rooms at their operating temperatures. One common system is the vapor compression cycle, in which the working fluid, called refrigerant, undergoes different processes. Compression, that requires electric power to be provided to the compressor, condensation, where heat is rejected to the ambient, expansion, through an expansion valve, and evaporation. The evaporation process is of particular interest to us, as it allows the heat removal from the cold room, maintaining the temperature inside to the set point. Therefore, calculating the heat that has to be removed by the evaporator is a crucial factor to properly design the refrigeration cycle and assess the corresponding power consumption. The calculation of the refrigeration load, QR, and mean refrigeration system capacity, QSYS, depends on different variables. The mass of the food that has to be frozen, mm, the specific heat capacity of the food, Cm, the initial temperature of the food, T1, final temperature of the food, T2, the heat gain from the ambient through the room surfaces, wall, ceiling and floor, QWV, the heat gain from air infiltration depending on the opening of the cold room door, air changes per hour, QI, the heat gain from equipment and lining, QM, the target freezing time, the time required to reduce the food initial temperature to a target final temperature at the slowest cooling location. It may be either calculated from theoretical models such as the Planck's one, or set by the designer to ensure food safety and quality. Through this equation, we can preliminarily estimate the refrigeration load and the mean refrigeration system capacity that is removed by the evaporator. Once the mean refrigeration system capacity is computed, the electric power that needs to be provided to the compressor can be calculated. The efficiency or COP of the cycle can be calculated as follows. Hence, the electric power required by the compressor can be calculated as shown in this equation. Let's now try to calculate a real existing cold room. Find the refrigeration load and average evaporator capacity required for chilling in 12 hours 120 kilograms of meat, beef, from 39 Celsius degree to 4 Celsius degree, considering an outdoor ambient temperature of 30 Celsius degree and 80% relative humidity. The cold room temperature is kept at 0 Celsius degree. The specific heat of the beef is 3140 joule per kilogram Kelvin. The walls, ceiling and floor transmittances are 0.25 watt per square meter Kelvin, and the overall area is 16.16 square meter. The room volume is 4.22 cubic meter, and 5 air changes in 24 hours are assumed. The power required by the fans and the lights is 250 watts. The heat gain from the ambient through the room surfaces is about 121.2 watts. From a psychometric table, the enthalpies of outdoor and cold air are 85 kJ per kilogram of dry air and 9 kJ per kilogram of dry air, respectively. Then, the heat gain from air infiltration is about 22.7 watt, and the heat gain from equipment and lining is 250 watts. At this point, using equation presented for the load calculation, we obtain the mean refrigeration system capacity in this equation, which is about 699.2 watts. This is the refrigeration load that has to be removed from the cold room by the evaporator. Therefore, assuming a COP of 2.5, we can calculate the compressor power resulting equal to 279.7 watts. This power is consumed during the initial cooling of the meat from 39 Celsius degree to 4 Celsius degree. Then the refrigeration load for keeping it at this temperature reduces, and it can be calculated as the sum of the heat gain from the ambient through the room surfaces, the heat gain from air infiltration, and heat gain from equipment and lighting, corresponding to 393.9 watts, requiring 157.6 bucks consumed by the compressor. In this lesson, we have seen how to calculate refrigeration load required to cool down a specific amount of goods. Once determined, it is possible to proceed with the vapor compression system design.